Hello everybody. This will be your third theory lecture, and today it's going to be on the module Series Resistive Circuits. So, let's get into it. What we have here, this is straight out of your module, we have a series circuit. The first thing to remember about a series circuit is that we'll only have one single path for current to flow. So the current that comes from the source is going to go through the entire circuit. There's only one path for the electrons to go. If you remember from previous lectures, the electrons flow or go through the circuit from negative to positive. And in a series circuit, there's only one way for that to happen. Okay. If you remember, E is our total voltage. You may also hear it called the source voltage, right? If we have, that's where our EMF is created, our electromotive force. And then that source of electrical energy is where the electrons are going to come out of on the negative and back on the positive. You may also hear the E referred to as the applied voltage. So that's the total voltage in the circuit. That's the source of voltage or source of electrical energy in a circuit. It's also the voltage that is applied to the circuit. So those are the three ways you may see E referred to. I always like to touch on that. Sometimes they trick you up, or trip you up in questions by calling it something different. The IT, or this, write this bigger, also known as the I total. So the I is our variable. That's our variable for current. And this T is called a subscript. It's just saying which I it is. So that's the I total. Throughout the circuit, you have V1 and I1. So that's the voltage and current of this particular point, right? That is I1. I1 is the current at this particular spot, and V1 is the voltage at this particular spot. So here we have a different way of laying out that same circuit we just looked at. This is figure 3 from your module. It's the same circuit as figure 2. So if we look at it, we have E up top with our negative, and the current's going to come through the circuit. There's only one path for it to go still, and it's going to come back up and return to the positive. Right? Electron flow, and our current flow, because where electrons flow, current flows, goes negative to positive. So it looks a little different. This is right. There's a ladder style. They call these sides, I think these are called the rails, and this is a rung, sort of like if you want to think of it like a step ladder. But just know that it's the exact same circuit. There's still only one path for current to flow. It's still a series circuit. And always remember that there's a difference between a V and an E, because E is our source voltage or total voltage, and V is going to be a specific measurement at this location. Okay, so we're going to start doing some calculations with the volt drops. Then we have R's in this diagram. They could have drawn them on the last one, but they didn't. Doesn't matter. Remember from the last lecture that R is a fixed value. So when someone made this resistor, it got made with a specific resistance value. Okay, that's not going to change until that resistor breaks down. Now let's look at some of the rules, sort of the mathematical rules, if you want to think of it that way, for a series circuit. Excuse me, in reference to E, or I should say V, R, and I. So these are, I like these rules because they're the same in every series circuit. If you remember them, you can solve any of the series circuit problems once you get comfortable with the math. So, reiterating that there's only one path for current to flow. Okay, so one path for current to flow. We have 3 resistors. That's just what they drew for this circuit. We have 3 resistors, R1, R2, and R3. So if we ever wanted to find the total resistance, that's just an R with the subscript T. If you think about current and resistance and their relationship, resistance is the opposition to current flow. So this, they're showing an arrow that just shows current. So this current is going to flow through this resistor first, then resistor 2, and then resistor 3. So by the time it's going back to the source, it's gone through all of those resistors because there's only one path for current to flow. And so the total resistance of the circuit is quite simply R1 plus R2 plus R3, because we have 3 resistors. If there was just 2 resistors, it would just be resistance total equals R1 plus R2. So that's the total resistance for a series circuit. Just add up all the resistors, and that's your total resistance, okay? I total, because there's only one path for current to flow, well, at every point in the circuit, the current will be the same value. So I total is the same as I1, it's the same as I2, it's the same as I3, right? At this point, at this point, at this point, in this entire series circuit, the current will be the same. So if you were doing a math problem or some kind of problem they give you for a series circuit and you find I2, well, you just found I1, I3, and I total as well, right? All the currents will be the same. Now, voltage is where it's going to get, it's not tricky, but it can trip you up if you're not careful. So, Kirchhoff's voltage law, that's our second law. We started with Ohm's law, right, which was I equals E over R. Now we have Kirchhoff. And what Kirchhoff's voltage law is, the voltage rises must equal the sum of the voltage drops. If we were going to mathematically represent that, which I recommend you doing, we would say E equals V1 plus V2 plus V3. Now that does look pretty similar to R total, but R total is just adding up these 3 resistors. That's just the fixed value. Kirchhoff's voltage law, the way I believe he originally wrote it, is that the sum of the voltage rises, forgive me if I'm repeating myself, equals the sum of the voltage drops. So this is another way to represent the exact same equation. Or, sorry, not the exact same equation, the same result, because the voltage rises, which is our applied voltage, right? Nothing happens in this circuit until we apply a voltage, and then that is the rise in voltage. If this was 120 volts that we just added into this circuit, and then the voltage drops off at each resistor, well, the only rise, right, because each of these is a voltage drop, the only rise in the circuit is E, where we applied the voltage, where we added in a source of electrical energy. Now we have a voltage rise, which is 120 volts in this situation. I'm just using a common number. And so 0 is going to be equal to that applied voltage minus the other voltage drops. So Kirchhoff's law is that what we apply to this circuit will get dropped throughout the circuit, and it will equal 0 in the end. Now, this is all these images are just taken right out of your module if you need a frame of reference. So now we have some voltmeters set up measuring different spots and different points of this circuit. So it's the same circuit that it's the only circuit we've looked at so far in this lecture. This is still that ladder style diagram, right? One path for current to flow, which means it's a series circuit. And so what each voltmeter is measuring is, obviously voltage, but remember that voltage is a potential difference. So if we look at this one at the top, that's labeled E, it's measuring the difference between the start or the beginning of the circuit to the end of the circuit. And so the difference from start to finish is 120 volts, right? That's our applied voltage. Each of these voltmeters, V1, V2, V3, are measuring the voltage before and after a resistor. So what they're measuring, we say, is they're measuring a volt drop. So the volt drop at R1 is 32, and then 46 at R2 has a question mark for V3. Well, I'm going to bet it's 120 minus 32 minus 46. That's going to give us this last volt drop, because in total there's 120 volts in the entire circuit. And according to Kirchhoff, that 120 is going to get dropped off throughout the circuit. Okay, so that's a good diagram just to highlight his voltage law. Now we're going to talk about ratios, which may sound like a total left turn. Why the heck are we talking about ratios? We were just talking about Kirchhoff and Ohm and all these circuits and such. It's going to make sense in a minute, but just stick with it. Ratios are a really important way of understanding how all these laws and voltages and how everything interacts. Ratios are going to help you understand it a little bit better. So ratios is comparing, to me at least, it is comparing mathematical values or expressions. Hopefully I can spell. Hopefully I'm a better electrician than a writer or a calligraphy person. Anyway, so a value is, for example, 1. 1 is a value. An expression could be 1 plus 1 equals 2, right? So we're comparing values. Oops, sorry, that's values or expressions. That's supposed to be an or. So how they show it in ratios, or how they show ratios, is something like this. 1, 2, 2. That's one way. They might also do 1 colon 2, or they might do 1 over 2, which you might recognize as a fraction or also division, right? 1 over 2, you could also say is 1 divided by 2. But all the same, these are equal to each other. They're just different ways of representing ratios. And the order of the ratio matters, because 1 over 2 equals 0.5. That's 50%. 2 over 1 is equal to 2. That's completely different, right? So the order of your ratio matters. Now, let's talk about one other sort of thing related to ratios, which is direct proportions and indirect proportions. And let's relate it to exactly what we've been working on this whole time. Let's relate it to Ohm's law. I'm a big fan of Ohm's law. I like how simple it is. I like that it's consistent. There's not a lot of laws you can consistently count on. I mean, most laws are okay, but anyway. E equals I times R, right? That's another way of writing Ohm's law. If we transpose Ohm's law, we can get this. So E equals I times R. Now, if the I increases in this formula, the E will also increase, right? If you have 2 times 2, that would be 4. If you have 3 times 2, that would be 6. Now, at the same time, if I goes down or decreases, E would decrease, okay? And that would be a direct proportion. Those are directly proportionate to each other. Same thing with R. If it goes up, E goes up. It goes down, E goes down. So that's direct. Indirect, if we want to keep using our fabulous Ohm's law formula, I'm going to write the other 2 ways that we learned how to transpose Ohm's law. Right. If R increases, then I will decrease. Okay, and vice versa. If I increases here, then R will decrease. And the only reason is if the denominator is larger, right? Just like we were looking at this ratio up here. If the denominator is larger, the numerator, the number that gets divided by the denominator, the numerator will be reduced more, if you want to think of it that way. But just know that in this type of equation, these are indirectly proportional. So if I goes down, R will go up, and vice versa on the other side here. So now let's talk about what's called the voltage divider rule. It's essentially playing with ratios, but just once again, I'm going to go over some of our rules of a series circuit, and then we're going to see why this voltage divider rule works. So if you remember, I total equals I1, which equals I2, right? So our current here is the same as our current here at I1, which is the same as our current here at I2. And if we look at Ohm's law, just for this load, we would say I1 is equal to V1 over R1. We can't say that E, or our total voltage, is equal to I total times R2, because that's leaving out R1. It would have to be R total. So I1 is equal to V1 over R1. But, I mean, in the simplest words, I is I is I. And I'm not talking about myself. I'm just saying that the current is the same everywhere. So if I1 equals V1 over R1, and I2 equals V2 over R2, and I1 is equal to I2, then we could also say that V1 over R1 is equal to V2 over R2, right? Because whatever the values of these 2 variables is going to be equal to I2, but I2 is the same as I1. So whatever the value of V1 and R1 is must also be equal to I2 or I total, because it's a series circuit. Current's the same throughout the circuit. So that's the voltage divider rule that they're talking about in your module. It's saying that V1 over R1 is equal to V2 over R2, and if there was another resistor in this circuit, we would be saying that V3 over R3 is equal to the same thing, because I total equals I1 equals I2, pardon me, which would be equal to I3 as well if there was this third resistor, right? So that's your voltage divider rule. That's an important one to remember. It's going to help you save time when you're solving these series circuits. So let's go through a question together. I believe this figure is also solved in your module, but I figured it'd be good to just demonstrate maybe how I would think about it. So usually what these math problems are is finding the missing variable. They're going to give you some values, they're going to give you a circuit, and they're going to say, what's this? So here it's saying calculate current flow, right? So yeah, it doesn't give me any I values, but it does give me the value of each resistor, and it gives me my source voltage. Okay. So I know that I total is the same as I1, which is the same as I2. So if I wanted to just solve this whole circuit, I'm going to want to get my I total because I don't have any current, and I know once I get my current, well, that current's going to be the same everywhere, right? That's one of the nice things about a series circuit. So I know that, according to my friend Ohm, I total equals E over R total. If we're going to do E, we have to do R total. I could do I1 equals V1 over R1, but I don't have a voltage yet. And I'm not going to be able to find out what the volt drops are without a second value to go with these resistors, because V2 is going to be equal to I2 over R2. Oops, sorry. V2 is going to be equal to I2 times R2. My apologies. But if I don't have I2, well, then I can't figure out what the volt drops are. So I need total resistance. But thankfully, they gave me resistance values, so the R total is just equal to 20 ohms plus 40 ohms, right? You just add up all the resistance, you get your total resistance for a series circuit. So R total is 60 ohms. Nice and simple, nice and clean. So I total, now I can figure this out, is equal to 120 volts over 60 ohms. It's our friend Ohms who is coming to help us. And my I total is therefore going to be probably 2 amps. Which means now I can figure out V2, because V2, or the volt drops across the second resistor or across the second load, is equal to 2 times 40. Put our units in there. So my volt drop there is going to be 80 volts. So I already could make a pretty good guess that V1 is going to be 40 volts, because 120 minus 80 equals 40. If you wanted to prove that in a different way, you could go right back to our friend, Mr. George Ohms. I think his name is George. And you could do V1 is equal to I times R. And we're at the first one, so it's I1 times R1. B2 times 20. And then V1, the volt drop there, look at that, it's going to be 40 volts. So Kirchhoff and Ohms agree with each other, which is nice because they have some laws we need to know. Now, the end of the module has a pretty good critical thinking aspect of all this stuff that we just learned, or I call it critical thinking, depends how you want to look at it. So, same circuit, except now we have a switch, right? It's the same circuit that we've been working through in the whole module, but now we have a switch. And this is a symbol for a closed switch, and this is a symbol for an open switch. So what the question is what is the difference between these two circuits? When the switch is, and we're going to assume this switch has zero resistance. We're kind of just, it's in the classroom, we're going to be using ideal circumstances most of the time. For example, if you go to a receptacle in your house and you safely safely, put a meter across the live side and the neutral side, you're probably not going to get exactly 120 volts. If you do, send me a picture. That's pretty crazy. It's probably going to be 119.8 or 122 or 122.9 or something like that. So just know in the classroom, we're just going to deal with ideal situations to get the concepts down. Excuse me. So ideally, a switch has no resistance. Okay? And so you've heard me say too many times, I'm sure, that voltage is a potential difference, right? This 120 volts is measuring from the start to the finish, blah, blah, blah. I go on and on. But what's important to remember for this situation, these two circuits, is if this switch is closed, then the voltage across the switch is going to be 0 because there is no potential difference from either side of the switch. Electrons are coming in, they're going out. They don't care about a switch. They just want to go. They just want to go, and then the electrons want to come back and meet their buddies. Okay, so they didn't label this diagram, but we will. So there's a negative to a positive. The switch is closed, who cares? But if the switch is open, well, now the electrons cannot get through. Now we do have a difference from either side of this switch. Now your voltmeter is going to measure 120 volts. Okay? Because the difference, right, the voltage drop, if you want to say, across this switch is 120 volts. Measuring from here to here is the same as if you took your leads and you brought it down here, then you went all the way around and you measured right here. That's the exact same thing because this is now an open circuit. So that's series resistive circuits. The next one will be parallel resistive circuits, and then we're going to put both of those together, and I'll see you in the next lecture.